We would now like to find a method that puts the coefficients, or some of the coefficients, exactly to 0 as we increase regularization strength. So we have to define an objective. And this third method of the day is called Lasso Regression. Why Lasso? I think the idea is just, some of the slopes that go wild, you catch them with the lasso. I think that is the picture. The authors are from California. And actually one of the authors of our favorite textbook for this course, that was the inventor of the lasso, so Rob Tibshirani. It was invented in parallel by Donohoe in signal processing. So it was a method that popped up simultaneously in several places in the late 90s. Okay. So to get truly sparse coefficients, what we would like to solve is something like the following. We would like to use the L0 norm of beta. What is the L0 norm? It is simply the L0 norm it counts the number of non-zero components. So if I try to draw a picture of this, let's say this is beta 1, this is beta 2, and the zero norm of this, it would be 0 here, and then it would be 1 along these axes, and it would be 2 through the rest of space. And now remember that with ordinary least squares, we had already found how our sum of squares increases as we go away from our optimal parameter estimate beta hat. And we plotted pictures like this, where we were saying this is our optimal parameter estimate beta hat. And now as we go away from this optimal parameter estimate, our sum of squares increases. But you see, this is now not so trivial to evaluate under the L0 norm. So essentially, I would have to, these are meant to be ellipsoids here. So essentially, I would have to try out what is the smallest value that I can find along a few places. I would have to evaluate what's the loss at the origin, at the green point, because, well, if I want a solution with 0 coefficients, so I'm just saying there's no dependence of my y on the x at all, then I will not incur a loss from my regularization term, but I will incur a loss of, well, you can read it off from these parabola or from these ellipsoids here, excuse me. I could read off what's my loss if I simply set beta to 0 and that's it. Yeah? Or I could say, okay, let's use only beta 1, and then my optimum solution would be here, and then I would have to evaluate how big is that loss. Or I could say, let's use only beta 2, and then probably that would be the optimum. Or I could say, fine, let's use beta 1 and beta 2, and then the optimum would be here. So now it depends on the value of lambda which of these values is actually best. But between the two blue solutions, I could single out the better one. I could say the solution that uses beta 1 but not beta 2 is always better than the other one. But still I have to compare three solutions. I have to compare the red solution, one of the blue solutions, and the green solution. In that sense, it is combinatorial. It's try this and try that and try that. Now, trying out three solutions is no problem, but as we go to higher dimensions, there's this exponential increase in number of solutions that we have to try out, and the problem becomes hard. So this is why instead of the L0 norm, there is a desire to use something which is more tractable. And instead of the L0 norm, one could use the LP norm. So this P in the LP norm has nothing to do with the P, the dimensionality of our problem. So this is a bit unfortunate, but this is how it's called in the literature. Yeah? So the LP norm would be, this is really unfortunate. I'm going to have two P's with different meanings in one equation. Let's use a different letter here. Let's call it the L norm, even though nobody uses that. Yeah? Okay. Now I go from 1 to, we usually call P the number of dimensions, and then I would have beta I, and I take it now to the Lth power, and then I take the Lth root of this. Or I can say here to the power of 1 over L. And we can look at a few pictures. Probably it's a better idea for me to use pictures from the internet, but I'll try. So I'm making this up now. Yeah? So let's say for L equals 0.1, I'm drawing the equicontour lines here. They would look something like that. Again, equicontour lines means the set of points that have the same distance from the origin as measured by this, what's usually called the LP norm. Then, now to simplify the plots, I'm going to draw only one of these isocontours because otherwise it's going to be too messy. Then we have the L1 norm, where our isocontours look like that. We have, of course, the L2 norm, which would be a circle. We have the L infinity norm, which looks like that. And these other fractional norms, they somehow interpolate. So we could use a 1.5 norm or so, which would be somewhere between the green and the red example here. Now these are the, let's stare again at our sum of squares. So the sum of squares is y minus beta transpose x times y minus beta transpose x transpose. I'm going to write it out for once. Okay, this is a function of, so given x and y, this is a function of beta. Sum of squares of beta given the x and the y's. Okay, now to this sum of squared residuals term, we can now add one of these potentials. And in general, this is an optimization problem. In general, when we solve optimization problems, the difference between easy and hard is not the difference between, is not the transition from linear to nonlinear, but it's the transition from convex to non-convex. So we are interested in using convex regularizers, if possible. So let me try and make similar plots here in one dimension. So I'm just now in one dimension. That doesn't work. So either you have a very good geometric intuition, or you have to take my word for it, that L equals 1 is the watershed. So for these norms, our optimization problem is non-convex. And for these, the problem is convex. So we are using the LP norm, or the Lasso uses the LP norm, which is closest to the L0 norm, but still just about convex. So in other words, for the Lasso, we are going to minimize over beta this thing plus the L1 norm of beta. You don't like me erasing stuff, huh? Sorry. Some people hate it. Good. You know. It should be beta transpose xy transpose. Thank you. Yeah, when I do stupid things, then please complain, okay? Like erasing things. All right. Let's look at this one norm of beta. I'm going to draw a few more isocontours just for it. So this is beta 1, this is beta 2, and now I'm going to draw in green here the L1 norm of beta, and this is what it looks like. And by the way, in the definition of the LP norm, I forgot to put absolute value. Okay, it's absolute value of beta I to the power of L. Excuse me. Okay, so there was a mistake there. Now, what we see here are 4 planes. So on this side here, or I can make, I can now distinguish 4 cases in this 2D example. Huh? So here it would be beta 1 plus beta 2. Down here it would be beta 1 minus beta 2. Here it would be minus beta 1 minus beta 2. And up there it would be minus beta 1 plus beta 2. So in other words, I could write all of these things as just formally. Yeah, I could write this as a function of a vector A depending on beta, A transpose times beta. And this A of beta itself, that is either minus 1 or plus 1 to the power of p. But the important thing is that in each of these 4 quadrants is just a plane. Okay? So it's just a plane in each of the quadrants. So in other words, I could also here replace this thing by writing plus A transpose beta, and I'm putting a small dependence on beta here to say that, well, this depends on which quadrant we are in. What I try to highlight when I write it here in this form is that in each of the quadrants, my sum of squares plus this regularizer is still just a parabola. So what we have here, the first term, this is a parabola. And these things here are different planes in each orthant. And as a consequence, what we find is that our objective, a parabola plus a plane is a parabola. So what we find is that the objective is just a parabola in each orthant. And moreover, these parabolae are meeting up because this function, this L1 norm of beta, it is continuous at the places where we go from one orthant to the next. So these parabola match up. They match up at the orthant boundaries. And now comes the important part with the convexity. Thanks to convexity, we have actually a single minimum. So the first two statements just say we have parabola, a different one in each orthant, and they match up. But the first two statements could still permit different minima in the different orthants. But thanks to convexity, we have a single minimum. You cannot read something. Can you ask me? Parabolae. This one here? Parabolae, a plural of parabola. So the objective is just a parabola in each orthant, and the parabolae match up at the orthant boundaries. Thanks to convexity, we have a single minimum. Yeah. Orthant is just the generalization of quadrant to higher dimensions. Okay, let's look at pictures. go. So, some example. Here are my axes, beta 1 and beta 2. And what we see on the left-hand side is my parameter estimate. This would be beta hat. And indicated by these isocontours. So all of these isocontours here, they show me how the sum of squares increases as I try out different values for my parameter. So how good a fit is it to the data? And the sum of squares is quadratic in beta. So the isocontours are all ellipses, and overall the thing is a parabola. No? So this is a parabola here. Now let's pick a pretty, if we set lambda to infinity, then we only see this regularizer. We see those isocontours that you see of the L1 norm of beta. These are 4 planes, and well, the single optimum is to just set all the coefficients to 0 and be done with it. Now, the more interesting cases that are in between, let's look at this one here. Here, lambda is large. So I'm adding up my parabola with this L1 term. So I get 4 different parabolae which match up at the boundaries. You see the isocontours here, they are nicely continuous at the boundaries of the offense. I get 4 different parabolae, and we can still see in each offend it is a parabola, but here the minimum also happens to be at 0. So here lambda was large, but here the optimum solution still is to set both beta 1 and beta 2, beta 1 and beta 2 to 0. Now, if we reduce lambda further, there is now an interesting case. You see, now we have a 0 value for beta 2. So here, beta 2 is 0, but beta 1 is not 0. And geometrically speaking, still the same thing. It's still 4 parabolae which match up at the offense, but now the global optimum happens to be where the cross is. All right, and if we do this for, let me look for, where's the example? There. I'm going to push this up. Let's compare this to what happened at Ridge. Remember, this was the example from Ridge regression. As we increase regularization strength, parameters eventually became smaller, but they only become all 0 in the limit. Now for this new loss function with the L1 regularization, here's the result. On the right-hand side, we again have the ordinary least squares solution. And now we increase lambda as we go to the left. And here you see that the coefficients, they can still cross over as before. But now the coefficients become strictly 0. And if we look at h specifically, here it does not cross over and suddenly have a positive contribution, but at some point it just dies out. And if we look more closely, then by the way, we see, and it can also be proven, that these changes here are piecewise linear. So because they're piecewise linear, actually we only need to compute this for values of lambda where one of the things becomes 0. And we can even compute when it will become 0. So we can start from the ordinary least square solution. Then we can estimate what's the gradient of all of these changes of magnitude in coefficient. And then we can compute when will the first one go to 0. That's that one. And then at this point, we estimate all directions again. And we extrapolate linearly until the next one becomes 0. And so on. And that's also the basis of a very efficient algorithm to compute these things. Yes?
But in general, I can't see a difference to the ridge algorithm because there you also can set a threshold or something and define when the first coefficient becomes lower than the threshold and nearly 0.
So we could, of course, use a threshold. We could say we define a threshold maybe like so, and we exclude everything inside the threshold. But if we look at h, let's make this a little bit smaller, this threshold. So then I would need two parameters. One parameter would be to say what's the value of lambda, and the other parameter would be the size of this exclusion zone. And if we look at age, then for some values of lambda, it's significant, and then it becomes insignificant, and then it becomes significant again. So that would be a bit of a problem. Plus, we have this one more parameter. I think it's not, your suggestion is not a bad one. But in the example shown here, even for very strong regularization values, most everything would be outside the threshold. So fundamentally, it just does not have this nature, it does not have the sparse nature, the solution. And I would like to give you another geometric intuition for why that is so. So why sparse solutions? I'm now going to show you a very famous picture from this kind of literature, which is this one here. So let's say that the black things here are the sum of squares. And here are the regression coefficients, beta 1 and beta 2. And if we now start regularizing more and more, we shift our estimate. Yeah, initially our best estimate is right there. This is beta hat for lambda equals 0. And if we now crank up lambda, in this particular example here, this matrix is an isotropic one, then this extra plane that we have will shift our optimum in this direction, and it will eventually, so we're shifting our optimum now in this direction, and it will eventually hit this point where one of the coefficients has become 0. Yeah? So another version of the same picture essentially is as follows. We can say that we have some sum of squares estimate, which depends on beta. And for all of these objective functions, there are always two equivalent formulations. I could give a constraint formulation also for ridge. For ridge, it would be to minimize the sum of squares over beta, such that the L2 norm of beta is less than some value, not lambda, but I need a different letter here, let's say kappa. And for the Lasso, it would be the same thing, such that the L1 norm of beta is less than kappa. And I'm now going to use this constraint formulation. So let's say ridge is now red. I'm going to use this constraint here. And if I'm now looking for the beta which has the lowest sum of squares but still lies in this disk, then the point or the solution that I find is this one here. So this would be beta ridge or beta head ridge. But if, on the other hand, I am asking my circle was not a nice circle, excuse me. But if, on the other hand, I'm now asking to be somewhere here in this, what is it, a rhomboid? Then the optimum solution will be there. So this would be beta hat Lasso. And do you have a question? Yes.
Yeah. What does ST stand for in this context?
ST, such that. Thanks. Okay. And yes, go ahead.
Why do we get a unique solution if the red curve has two intersections with the bundles of the sum of squares?
Why do we get a unique solution in the case of ridge or in the case of Lasso?
Both. Because we have always two intersections of the bundle.
So we are, remember that the sum of squared things, this is a parabola located here. And I'm going to draw it a little bit differently. In the case of ridge, we're now saying we're looking for the optimum solution which lies anywhere inside this circle. And so our constraint set is convex, and our objective function is convex, and then that gives me a single solution. It can be ambiguous, and sometimes it could be like a valley, but there's a single solution. Okay? All right. So why this sparsity, or why do I get a single? Let me draw a final picture for you, okay? And then I'm done with these pictures that are practically always showing the same thing. I'm going to now pretend, so for sake of argument, I'm going to pretend that x transpose is isotropic. Or that means it has degenerate eigenvalues. So that means that the sum of squared parabola will be perfectly, or the isocontours will be concentric circles. And if I'm now creating this constraint set again, let's say this is my constraint set. Where this here is some value kappa. Now I can ask for where can my solutions beta hat lie such that they will map onto one of the corners of this geometric body. And the solution is as follows. I have these two regions, or these two kinds of regions. In these bright green regions, those are the regions of beta hat OLS, which will give sparse beta hat Lasso. Why? Because if I, for example, put my beta hat here, and then I have these, concentric circles along which my sum of squares increases, then these convex circles will first touch my constraint set in one of these vertices. But if, on the other hand, for example, my solution beta hat is here, and I have these concentric circles, then the first point where it will meet the constraint set would be not at the corner, but along one of these faces here. And that solution is not going to be sparse. This is why I get these four regions of space where solutions are sparse or non-sparse. Now, as I make lambda bigger, my kappa becomes smaller, and so overall, the fraction of sparse solutions will become ever larger as I increase lambda or as I make kappa smaller. Do you have questions? Yes?
Just a question. So, have you made any assumptions for the noises in data?
The assumptions for the noise in data are the same as for ordinary least squares.
So, Gaussian noise?
We didn't make the Gaussianity assumption. Even in ordinary least squares, we only said that if the noise is Gaussian, then the posterior will also be a Gaussian. But for the sum of squares, we don't need the Gaussianity assumption. More questions? Okay, I have one more thing that's both interesting and also you will need for the exercise. Namely, I want to show how computer tomography reconstruction is actually an example of linear regression. So computed tomography, CT, is an instance of linear regression. So how it works is we have some unknown body. Let's say if we're in medical imaging, this could be a skull. And we now send X-rays. We can invent different geometries, but the simplest geometry to reason about is just parallel X-rays. And then we have a plane detector. And then this detector will record an absorption that's a function of space. So the way I sketch it here, the signal that I will receive are a couple of, scalar measurements. Now, if we want to do a 3D reconstruction, or here a 2D reconstruction, then I need to rotate both my source and the detector in a gantry around the object of interest. And let's look at our skull in a bit more detail. Let's say I pick this X-ray here, and we want to discretize our medical image. So let's say these are the pixels of the medical image that I'm trying to reconstruct. Then the unknowns, beta hat, are the absorptivities, or let me call it here, the intensities of single pixels. The curve that I measured, this absorption pattern here, those were my measurements y. And now the x is going to tell me to what extent my particular measurement, or my single X-ray, interacted with each of the pixels in my image. So I can see that, for example, this pixel here had that much of an interaction with my X-ray. This pixel here has zero interaction with my X-ray, because the X-ray didn't go through it at all. This pixel here has a larger interaction with my X-ray, because the X-ray passed longer through that pixel. Now we can collect all of these things in a linear system. So we have a huge column vector. Its entries are 1 times the number of rays. And it has the measured intensity for each ray. And we're going to try and explain this as a product of the unknowns. So this would be y, and then we have beta transpose. The number of entries here is the number of pixels in the image, which is hopefully smaller than the number of rays. And we have the measurement matrix, X, which tells us about how much does each ray intersect with each pixel. So the dimensions are number of pixels times number of rays. And the rays could be in a very general geometry. Yeah? So the way I've drawn it here, we have a couple of rays that went from the bottom left to the top right corner. But we can also have rays that go from the top to the bottom and so on. And all of these rays, wherever they come from, all of these measurements, we all compile them in a huge linear system. This matrix X, the measurement matrix, we are going to supply to you so that you don't need to compute that interaction yourself. We will also give to you these recorded measurements. So this would be, this, if we vectorize it, would become Y for some object. And your task will be to solve this linear system for beta hat. So Y will be given, X will be given to you because we know the geometry of our X-ray system, and you will compute beta hat. This is what's wanted, and you can try with ordinary least squares, but you will fail. And then you can use some of the regression techniques that we've seen today. Good. Now that was a lot of material. Thank you for your attention. See you on Wednesday when we will finally move to nonlinear regression schemes. Thank you.